Hey there, guys. This is Mr. Sheeline. I'm going to quickly just kind of walk you through, really just speaking um, over the 2.1 notes here when we're looking at the early atomic discoveries. So, if you're watching this, most likely you've been quarantined or you're at home. You just happen not to be in class. So this is I'm really just reading through uh, these notes. So if you don't want to watch this, go for it. But if you'd rather, like, if it helps listening to me, awesome. Because usually this is all I do in class. We kind of discuss uh, how it is that we came up with the atomic model that we use today. Um, and then I've got a couple demos that I do in class. So if you aren't there in class, it kind of sucks because you're missing out on a few demos to kind of help tie this in. So I'm just going to go ahead and read through this. So this is like the second, you could say part two of the 2.1 notes. We're looking at the early atomic discoveries. And these were like arguably the biggest atomic discoveries, the biggest, what could you say, contributions to putting together what life, what matter is made of. So we go all the way back to Aristotle, 500 BC. Aristotle believed that all things were made of something, that they were made of the four basic elemental forces, such as earth, air, water, and fire. And this was nothing new. This was he isn't the one who so much came up with this as he was, because it was part of the mythology, the what you could say the religion at the time, and it was it was something that he pushed forward, and he was like, what they called science back in the day. This is the science of today. This is how we were put together through air, fire, water, and earth. That's where all things are contrived, all things are comprised, I should say, all things are made. You then fast forward a couple 50 years, and you have a man by the name of Democritus that, in um, a drunken stupor at a party, which he was quite known for, as far as I understand, thought that all matter was made up of small, indivisible particles that he called atoms. So this is where we first get that word of atoms coming from. So 450 BC. So remember BC. Off the top of my head, I can't remember what exactly that Latin is, what BC is, but we all denote it for the most part as before Christ. So as of right now, roughly speaking, that is 2000, roughly 470 years ago from this moment right now that someone came up with that, which is incredible. Doesn't seem like it's been that long. Doesn't seem like it's been 2000 plus years, man, but humans have been walking for quite a while. So anyway, but he was the one who came up with the term atoms, which atom just means indivisible, roughly speaking. So problem was that this was just a concept. It was just an idea that he had. This wasn't something that he had any kind of proof of. There's really no way for him to prove it. It was just that, hey, I don't think that this earth, wind, fire, and water thing is right. I think things are made up of some sort of super small little thing. And how he came up with that is he was like thinking like, well, if you break down an apple, like an apple must be made of smaller pieces of apples, and you could break it down further and further and further until there has to be something that can't be further unbroken. And he thought of it with cheese. He thought of it with like wood, and he just said, "There's no way there's no way you could keep breaking a piece of cheese down, and it wouldn't be anything but cheese, and there would have to be a point in which it could no longer break." And that's where he came up with this atom idea. Fast forward a couple 2,000 years, we have Antoine Lavoisier, who is credited with being one of the just one of the naturalists and scientists ever exist. Anton Lavoisier, who just was a madman of science. It says discovered, composed, was able to put forward the law of conservation of matter and really backed it up with a number of different experiments that he did at a lot of like dinner parties and a lot of university presentations. And so what he used is he showed how the law of conservation of matter states that matter can neither be created nor destroyed. It is transformed from one form to another. So you just can't say I want apple and then boom, you've got an apple in your hand. It doesn't work like that. You have to it has to come from some sort of material that came before the apple for that apple to be a thing. And before that, something had to put that thing together, and something had to put the thing before it together. So it goes down to the idea of, like, you could say the law of conservation of matter is that silly phrase of that, we're all made of stardust. We're drinking dinosaur pee. It's exactly right. It's a bit silly, but it's exactly right. We're made of things that came before. We're made of things that were transformed from one kind to another kind. So, but anyway, Anton Lavoisier used bell jars to burn items and contain all the matter, so the solids and gases, and compared beginning and ending masses, and found in most of his demos to found them equal. Now, there are some that don't work out that way, and this is one of the demos you'll miss out on. This is when I do it's a burn and steel wool demo that's really cool because it kind of puts a little ratchet in there, and we kind of talk about, like, well, what's happening? Anyway, look that up. Just look up steel wool burning demo on YouTube, and you should get the gist of it. Then we have Joseph Proust, however you want to pronounce his name, depends upon the person pronouncing it. This man came up with the law of definite proportions. So again, weird way to say discovered, but put forward a law of constant composition. A given compound contains the same elements in the same proportion by its mass. So it's to say that, hey, we can calculate the mass of this. We can also calculate the mass of all the elements it should be comprised of, and the ratios that they should be comprised of. And we should see that there is exactly the same mass of, like, carbon that adds to the total of the whole thing based upon its ratio. So it's a weird way, I guess, of kind of listing that out. Think of it this way. If the ratio of a particular substance is 1 oxygen to 2 carbon, let's actually, yeah, we'll keep it with that. That the mass, when you measure out the mass, you would, and if you were to able to split up those atoms, they would split those pieces up, you would see that the overall mass would be equal to the combination of both the carbon and the oxygen. So why is that important? Well, that's important because it kind of tells you there's really no filler. There isn't any kind of mass found that gloms together that's formed between bonds of particular substances, that it is just the mass of the atoms. It's just the mass of that particular material, nothing else. Nothing else just kind of magically floats in. Okay, and then John Dalton, another just madman when it came to science, both in mostly physics. And John Dalton here proposed the atomic theory of matter. And so basically, we can break it down into these 4 portions. So that every element, looking at number 1 here, every element is composed of small particles called atoms. Number 2, all atoms of an element are identical, but different from those of any other element. Number 3, in any process, atoms are neither created nor destroyed. That's your law of conservation of matter right there. And a given compound always has the same relative numbers and kinds of atoms. We'll get into that, or we kind of got into that in 2.1 already, looking at isotopes. That's what that's kind of getting into. It's a given compound. So, a given compound always has the same relative numbers and kinds of atoms. So, sorry, that's not looking at, though it can deal with isotopes. It's more about what happens when you create a compound, when you break one down. And it's to say that, again, it's that conservation of matter, is that it's neither created nor destroyed. And it also goes to Joseph Proust, where the proportions of those are maintained from the beginning, before a reaction and after a reaction. So that this is just the basis of thinking about how it is that atoms may be put together, but that doesn't necessarily define its structure. So we've got a number of people to thank for that. So one of them being Benjamin Franklin. So Benjamin Franklin, kind of a man of all trades here, was also, I wasn't so much a naturalist as much as he was just very curious about the world and in a number of different places. And what he showed was obviously the electrical charges, his famous kite flying experiment, where he stuck a cup of keys on the tails of his kite to see if, hey, if that metal is what's going to conduct it. Not only did he do that, is that he noticed there were different metals that would conduct differently with the electricity. And what he saw was that there were electrical charges, roughly speaking, that he was able to say these are positive, these are negative charges. You notice that opposite charges attract, because if you put enough energy into something metal, and if you have a particular shape of that metal, you kind of create a magnet, and that those magnets interact with each other in particular ways. You notice that like charges repel, which is something we take for granted today. Something we get into in my physical science class and not so much in chemistry. It's electromagnetism is a really, really cool but very complicated field of study. It's really, really cool, but gets very thick with material. We have J.J. Thompson, studied cathode ray tubes. So what does that have to do with anything? Well, and why does Benjamin Franklin not discovering, but at least harnessing in some capacity or measuring at some capacity electricity have to do with atomic structure? Well, remember, what is the basic material? What is everything made of as far as we can tell? Everything is made up of atoms as far as we can tell. Okay, why does that matter? Well, it matters because electrical charges are going to interact with different atoms in different ways. Different atoms are combined together in different fashions that allow for electricity to run through them either better or worse. And this is something that J.J. Thompson also showed and was like, I was able to show here I can kind of funnel all the energy, all this high power energy. I can funnel it, and I can show you how I funnel it using this cathode ray tube, because again, this is how our atoms are put together. We have electrons on the outside, and we have, roughly speaking, that kind of buzz around in particular spaces around the nucleus. And J.J. Thompson discovered the electron by taking some gases, adding some electricity to that gas, and showing it basically illuminate. So, and he discovered and measured these electrical charges, because what would happen is that he would put magnets around these electrical charges and noticed that the light would bend. And this is a point where I would do a demo, is the Cathode Ray Demo. And it's a really, really cool demo that shows how completely tied together electromagnetism is to the structure of atoms. So what he did is he would shoot all this energy through, illuminate, he would light up these gases in this cathode ray tube, and he would take a magnet, and he would take specifically the negative end of the magnet, and he would put it near the tube, which is a glass tube. And he would show, like, if this is the cathode ray, and he would take the negative end of a magnet, what he'd see is that he would see the cathode ray would bend downwards, because we know that like charges repel against one another. And he was like, wow, that's really curious. And so he flipped it over and he took the positive end. And what he noticed is that when he put the positive end towards the rays, that it bent upwards. Okay. And roughly speaking, he discovered the electron. Now, he didn't really have a name for him. He was like, something in here is negatively charged and it's doing something here. Call them corpuscles is what he actually called them. And he knew that they had to be something. That were part of the atom, but just at the moment didn't realize what they were exactly, where they were at. And we come to Millikan. And Millikan measured the electrical charge. Millikan's the guy who said, here's this corpuscle, this electron thing that's here. Here's how much most likely the charge is. And he was able to figure this out by due to the distance between magnets of cathode ray tubes and the amount that the cathode rays would bend. with a number of other experiments where he showed this. And with that, he was able to, roughly speaking, calculate an electron's mass as well, due to the speed and the strength of the electrical and magnetic forces. So awesome. So we've got the mass, and by the way, the mass of an electron is virtually nothing. Like it's actually quite incredible. It's almost completely nothing, which is saying quite a bit when you're thinking about protons and neutrons that do have a significant mass. Electrons virtually have no mass. It's almost completely energy, if you want to think of it in that way. It's a bit more complicated than that, but roughly speaking, that's what it is. But anyway, Millikan was able to show this, and then Ernest Rutherford, who's one of, I would say, arguably the most famous with his gold leaf experiment. So, or gold foil, I should say, experiment. So what he did is that he took alpha rays, which at the time they knew alpha rays emitted some sort of, it emitted non-electron energy. Because what they saw was that it was something different, because when they shot off alpha rays, which is looks very similar in some respect to cathode ray tubes, but the only difference was that they were literally shooting it out of like a can, you could say, but they didn't have to house it in a vacuum sealed glass container. But they shot alpha rays, which are just, these are basically shooting protons. Is what they did. It's what they were doing. They were shooting the nucleus of particular substances, and they shot it at gold foil. And the reason why they shot at gold foil is because gold foil, gold is roughly, it's one of the more inert kind of metals, as far as when you're exposing it to the air. When you expose it to moisture, didn't really rust. It didn't rust. It does obviously get, you got to get it polished. It does lose its luster, lose that shine. But gold was great in the lab because it didn't basically degrade and rust like iron did and steel did. Even at this time they had steel, it didn't rust like iron. It didn't turn blue like copper did, and you could take a hammer, very, very easily smack it down into a very, very, very thin sheet. And the idea was the thinnest sheet you can get would be as close as you could to, the level of like a single atom. Like, so that's why they use gold so much, is because, again, you could flatten it out like crazy, very, very easily. Because remember, it only takes, like, I think, what is it? It takes a dimes. You can flatten out if you made a dime out of pure gold, you could flatten out that entire dime over the size of I want to say it's an Olympic or like professional size tennis court. It's been a while since I've heard that phrase, but it's something like that. And it's incredible. I mean, it's very, very malleable gold. So anyway, so Rutherford used gold to shoot atoms at, or these alpha particles at it, these alpha rays. And what he saw is that some would go through. And he noticed that some would kind of bounce off and would go in all these directions, and seemingly random directions, and some would bounce back. Okay. And then the way he was able to do that is he had these like little plates on the outside of his little setup, and the plates would capture all the points where the alpha particles were hitting. And so he was able to do that and show, like, wow, look at this. And so he calculated the angles, and he calculated the speed in which it would happen. And with all of that, he was able to determine, oh my God, the atom is mostly empty space. But in the center, there's something there. There's substantial mass in the center of the atom. And so he proposed and said, I just discovered the nucleus of an atom. So, and then from there on, it gets broken down even more. You could talk about Bohr. You could talk about Thompson, Bohr. My goodness. And now I'm blanking at the top of my head here. Other scientists, I'll just say it's early Sunday morning. Sorry. It's other scientists that kind of put the pieces together to formulate the structure of the atom that we think today. So anyway, it's a really cool, it's really neat the history of how it is that we came up with the structure of the atom, or I shouldn't say it that way, how we discovered, how we were able to prove that the structure of the atom is it's structured the way it is. Everyone between Aristotle and Democritus, again, like over almost 2,500 years ago to today. So really, really cool stuff. Sorry you get to miss out on some demos. Look them up. Cathode Ray Tube. It's really a TED Talk. There's a lady on that does a TED Talk over it, which is really neat. You look up the steel wool demo where you light up some steel wool while it's on a scale and see something really cool happening that you can talk about. All that good stuff. So if you guys have any questions for me, make sure you ask. If not, I'll see you in the next one. Have a good rest of your day.